let's do some examples that involve Poisson probabilities. So in this first example, we know that the number of traffic accidents per week is given to us as a mean with 3. It wants us to find the probability that exactly 2 accidents happen in 2 weeks. So the first thing we need to do is get the lambda for the Poisson distribution that we're talking about. So the Poisson distribution mean that they give us is per week. We want for 2 weeks. Well, the independence that we assume for Poisson distributions, that means that if we want the number of accidents in 2 weeks, we can just double the mean for 1 week to get that our lambda is equal to 6 for the Poisson distribution that we want. So now we're ready to answer the question that we were asked. What's the probability of exactly 2 accidents in 2 weeks? So we use our PMF for the Poisson distribution. Our lambda is 6 and our x is 2. So the probability that x is equal to 2 is e to the negative 6 times 6 squared over 2 factorial, which will give us 18 e to the negative 6, which in this case is answer B, since we have those multiple choice answers for us. Again, the point of this particular problem is the fact that we can convert one Poisson distribution to another by just looking at the time period. So again, in this one, the time period was per week given to us. We wanted in 2 weeks, so we just needed to double the mean to get our lambda for the Poisson distribution. And that is the big thing that we need for problems involving Poisson distributions, is what the lambda is. So let's look at another problem. This one, they give us at the second moment of the Poisson random variable as x. We want to calculate the probability that x is equal to 4. Again, we need the PMF for the Poisson distribution. The important part of that PMF is the lambda value. So our first goal here is to figure out what lambda is. So they give us at the second moment as 90. And we remember that for a Poisson random variable, we know that the mean and the variance are both equal to lambda. We also know that the second moment has to be equal to the variance plus the mean squared. Remember, one way to calculate the variance is to do expected value of x squared minus expected value of x, in this case mu, squared. So just rearranging that equation gives us this result that we want. So now we can figure out what lambda has to be, setting those two pieces equal to each other. We know that the second moment is 90. That has to be lambda plus lambda squared, just plugging directly in what we know. Lambda is the variance, lambda is the mean. Set it equal to 0 and factor, gives us roots of negative 10 and 9. Now again, Poisson random variables are numbers of occurrences in a time interval, so lambda can't be negative, or 0 for that matter. So we have to have that lambda is equal to 9. So now we can answer the question that we were asked. The probability that x is equal to 4 is, again, just plugging directly into our PMF. Lambda is 9, x is 4, and get 2187 over 8, e to the negative 9. And if you really don't like that number, you can convert it to a decimal to get about 0.03334. All right, let's look at a third example. This one's a little bit different. This one's asking us to calculate a standard deviation of a payment amount. So they tell us that the number of days of consecutive rain for a baseball team in April is a Poisson random variable with a mean of 0.6. So they already give us lambda. However, they're telling us that we have an insurance policy that purchases insurance against rain. It'll pay $1,000 for each day up to 2 days that the opening game is postponed. So if we want the standard deviation, of course, finding the standard deviation means finding the variance and taking the square root. To find those, we need to figure out what the moments are. So we need to figure out what the first and second moments of the payout amount is, not of the Poisson random variable, because we already know that. We know that the Poisson random variable, we know that the mean and the sigma squared, the variance, are both equal to the lambda value, which in this case would be 0.6. But that's not what we're looking for in this case. We want to know the payout amount. We know the payout for 1 day will be 1,000, and for 2 or more days will be 2,000. So we want to figure out the expected value and the second moment, the expected value of x squared, using that payout. So to that end, here's what the payout would look like for your expected value. If there's no days rained out, the insurance will pay nothing. If there's 1 day rained out, the insurance will pay 1,000. If 2 or more days are rained out, the insurance will pay 2,000. So now figuring out these values, of course, this first part's going to be 0. Here we're just using the PMF for x equal to 1 with a lambda equal to 0.6. So this is the probability that one day is rained out. Over here, we wanted to calculate 2 or more. Well, it's a lot easier to calculate 1 or fewer than it is 2 or more, meaning calculate 0 and 1 and subtract it from 1. Calculate the probability of the complement. So that's what's going on here. Here is where your x is equal to 0. Here is where your x is equal to 1. Calculating the two probabilities and subtracting it from 1 will give you an expected value of about 573-ish. Again, for standard deviation, we need to find out the second moment as well. Same concept, we just change these to squareds. Still have a 0 on the first part, doesn't matter if it's squared or not. Again, that piece doesn't matter. Here, same calculations that we just did an expected value of x, except that we've got squareds on the 1,000 and the 2,000. Gives us that number that's over 800,000. And now we want to get the standard deviation, so we do the square root of the variance. Variance is calculated as expected value of x squared minus expected value of x quantity squared. Plugging those numbers in, you see we get about 699. So the answer would be B. So in this case, a little bit different. One of the reasons why I put this particular example on here was getting you to understand that sometimes you need to calculate the probability of the complement, because if you did this one directly, you would have to do an infinite sum. And it's a little bit easier to do a finite sum and subtract it from 1 than it is to calculate the value of the infinite sum. Not impossible, just a little bit easier. Let's look at this particular example. Actuary has discovered that we've got policyholders that are 3 times as likely to file 2 claims as 4, and they tell us that the number of claims is a Poisson distribution, and they want us to find the variance. Again, like most Poisson distribution problems, the challenge is to figure out lambda. Lambda is the variance, so once we figure out lambda, we're done. All right. So the big clue here in this problem is 3 times as likely to file 2 claims as 4. So that, in math speak, is the probability that x is equal to 2 is 3 times the probability that x is 4. Using our Poisson PMF, we have e to the negative lambda, lambda squared over 2. We don't know lambda, that's what we're trying to find, but we do know x. Same thing over here on the right-hand side. Do a little bit of cleaning up. Your e to the negative lambdas cancel. You get lambda squared over 2 on the left, 3 lambda to the 4th over 24 on the right, or lambda to the 4th equals 4 lambda squared. You could go ahead and divide through by a lambda squared here, because we know that lambda can't be 0. If you were actually solving this equation, wanted all the roots, you would move it over to one side, set it equal to 0, and factor. If you did that root, you would find 3 roots. You would get lambda as 0 and plus or minus 2. But again, we're dealing with a Poisson random variable. Can't be negative, can't be 0, so we have to have lambdas 2. And like I mentioned at the beginning, that means the variance is 2, which is cut off at the bottom of your screen here. But trust me, the variance is 2, which is answer D. So, one more example here. The number of days an employee is sick each month is modeled by a Poisson distribution with a mean of 1. And we know the number of sick days in different months is mutually independent. Now we want to know if the probability that an employee is sick more than 2 days in a 3-month period. So the number of sick days in different months are mutually independent is telling us how to convert this Poisson distribution with a mean of 1 per month to a Poisson distribution for a 3-month period. If the mean is 1 per month, then the mean per 3 months must be 3. Okay, so we must have, now we want probability that you're sick more than 2 days in a 3-month period. Easier here again, if we want to calculate the probability of more than 2 days, x is greater than 2. I will do the complement, so 1 minus probability that x is less than or equal to 2. Well, just using our Poisson PMF with lambda is 3, we have x could be 0, x could be 1, x could be 2. Any of those values will work for x is less than or equal to 2. A little bit of simplifying gets you to 1 minus 17 halves e to the negative 3. The answer, of course, in the multiple choice is given to you in decimals. If you do the decimals, it's about 0.577. So hopefully this video will give you a little bit better idea of how you should attack Poisson distribution problems.